Let's go over the basics of predicting numerical responses. So this marks a pretty big shift from where we've been for the most part this semester, and that is with the task of classification, essentially predicting the level of some categorical variable. Is an individual going to click on an ad? Are they not going to click on an ad? Are they going to buy a product? Are they not going to buy a product? We have some levels and we want to classify individuals into these levels based on their characteristics. Now, regression is going to be the name of a task that we're going to focus in on for this unit, and it's concerned with predicting a numerical response. So how much money is a person going to spend during their purchase? How much money is that customer going to be worth to the company over the course of his or her lifetime, etc. And so we're going to put regression in quotes here because although linear regression is a model that we can use to predict numerical responses, the task of predicting a numerical response is generally just known by the word regression. So it's a much more general term. So surprisingly, almost every single one of the models that we've talked about so far can actually be applied to predicting a numerical response just with a little bit of modification. So let's talk about some of the terms that we need to know about what we'll be looking at for doing numerical prediction. It changes up a little bit compared with misclassification. There we were worried about AUCs, misclassification rates, accuracies, etc. When we're dealing with predicting a numerical response, here's what we care about. Well, first of all, we're still going to call the thing we're trying to predict our y variable and refer to that as our response. So for classification, y was a factor. For regression, y is going to be a number, like someone's GPA, the selling price of a home. Now, what we're going to use to make those predictions are going to be our predictor variables, which we've been referring to as x variables, just like with classification. And in machine learning, in general, people call predictor variables features. So we talk about feature selection, what's the best set of variables to make these numerical predictions. Now, when we go to evaluate our models and see how well they're making predictions, we're going to worry about how accurate our model is. But instead of the accuracy or misclassification rate, or AUC, like what we calculated for classification models, we're going to look at the typical size of the error the model makes. So there are two ways of doing this. We can calculate the root mean squared error, abbreviated RMSE. And that is just we look at the difference in the actual versus predicted values that come out of the model. We square those up, take the average over all the predictions that have been made, and take the square root. We get the root mean squared error. The other way of thinking about it is looking at the average of the absolute values of the errors. That's the MAE, or mean absolute error. And the difference between these two is that the root mean squared error is highly affected by a few really bad predictions. A few really big errors tends to skew the RMSE up towards big values. The mean absolute error is a bit more robust to a few bad predictions. It gives a better measure of the typical size of the error when a few of them are pretty large. Now, another thing we can look at is what's known as the R squared of the model for its predictions, and it's going to be a number that varies between 0 and 1. The closer to 1, the better the predictions are. It's essentially the square of the correlation between the predicted values and the actual values. And my very loose interpretation of the value of R squared is that basically using the model gets you about R squared of the way there to knowing the individual's value of Y. If it was 100%, then we'd be able to predict that individual's value exactly. All right, so we're still going to be concerned with the generalization error of our model. We'll estimate that with repeated k-fold cross-validation when we have the time to do so, or just standard k-fold cross-validation. We don't care about how well our models are fitting the individuals in the training data. We already know the answers to them anyway. And so our task is going to be to try out a whole bunch of models, estimate the generalization errors of all of them, and then choose the model that's going to have the lowest generalization error. Now we know there's some leeway with that one standard deviation rule. Our estimates of the generalization errors really are just estimates. They're just guesses. So we have a little bit of leeway over exactly which model we end up choosing. That one standard deviation rule narrows down all the models we've looked at to a set of acceptable models. Typically, just as a shortcut, we go with the one with the lowest estimate unless we have a good reason to choose another one. Maybe it's simpler or easy to interpret. All right, and just like what we had for classification models, there's actually a formula, now not one that you can just plug in numbers to, that discusses how the expected generalization error of a model works. And it's related to the complexity of the model and how realistic that model is for the situation at hand. We've talked about that the estimated generalization error of any model can be split up into three components: the variance of the model, basically how sensitive that model is to the particular set of individuals that happen to be in the training data; the bias of the model, and that's the systematic error that's induced by using a model to approximate a more complicated reality; and then the irreducible error. It's a measure of the inherent randomness of the process we're trying to study. Things are never perfectly predictable no matter what model that we use. There's always going to be some sort of uncertainty left over. No model can do anything about it. And so what we look at is, based on a model building procedure, well, what's going to be the variance and the bias of that model building procedure, and how is that going to affect the expected generalization error? And what we've learned is that there's a trade-off between these two. Basically, the more realistic we make our model, in other words, the smaller we make that model's bias, the more we leave ourselves open to having that model have a high variance. Why is that the case? Well, to reduce a model's bias, we basically have to extract out more and more information from the individuals in the training data to come up with a more and more realistic approximation to the relationships. However, the more information that we extract out of those individuals in the training data, the more we leave our model sensitive to those particular set of individuals in the training, thereby increasing the model's variance. So we can't decrease the bias of a model without increasing its variance, and the idea is that there's going to be an optimal complexity, an optimal amount of detail that we want to carry around in our model that's going to give us the best trade-off and the best expected generalization error. And that's what we're estimating with that repeated k-fold cross-validation. What are the set of tuning parameters that's going to give us the model that generalizes the best on new individuals? Now, there's one additional trade-off that we're going to have to worry about when making a numerical prediction, a model for that, and that is figuring out exactly what we should be predicting. Now, in classification, it's easy. It's just, is this person a member of the yes class or are they a member of the no class? But with regression, it's not that easy because it could be the case that we want to have as our response variable, our y variable, the raw data that's been collected, maybe the weekly sales of a product. But it might make more sense, and we might come up with a better model if we predict something slightly different. We might actually come up with a better model if instead of predicting the raw sales, instead of predicting the log base 10 of those sales instead. Maybe the distribution of the sales is highly skewed. Models tend to work better when they predict a response that has a symmetric distribution. So a model might be more successful if we predict the logarithm of the original values rather than the original values themselves. Or we might want to make some more in-depth transformations, or even just change the nature of what we're trying to predict completely. So maybe if we're trying to study the weekly sales of a product, it might make sense to let our response variable y to be the amount of weekly sales divided by the duration on which that product was maybe featured on TV, divided by the number of viewers that were watching it. So kind of looking at a velocity of the sales, a sales per time featured per viewer actually watching. Maybe that's easier to actually model or predict. We might come up with a more successful model. Or maybe we'll take the logarithm of that as well. The key thing is to doing a regression is really picking the right response to predict. Not always the easiest thing. Very often we try out a bunch of things and see what works. All right, so why is this important? Well, one thing that's important is to minimize the impact of outliers on our model. So one thing we know is that outliers increase the sensitivity, of course, of our model to particular individuals in it. And we know that it's a bad thing. That can increase the generalization error of that model. So consider the case where we have these three outliers here, which don't really follow in the stream of points described by the rest of the individuals. If we fit a regression, say, without these 3 points, we get this nice solid black line. With these 3 individuals, we get this red line. We can see how sensitive the model is to these 3 individuals. And we'd like to prevent that sort of sensitivity. So the hope is by sometimes doing those transformations, making a more symmetric distribution, we can minimize that impact. Now we can see that predicting something a little bit different, this is actually like the logarithm of the original values, we see that the shift between the line without the outliers and with the outliers is smaller than what it used to be before the transformation. So big shift, slightly smaller shift. We still see that it's still really quite influencing the model, but it's not as big. And that's what we're after. We're trying to minimize the model sensitivity to the particular set of individuals in the training data. That'll lead a model with a smaller variance and potentially give us a model that generalizes better. All right, so the first step of really doing a predictive model for numerical response is figuring out, all right, well, what are we actually predicting? Should we be predicting the raw values that are collected, the logarithms, some other transformation, something other that we construct? Once we know what we're predicting, well, we can see pretty easily how the rest of the models that we've discussed so far are going to tackle the problem. And so that'll be the next little YouTube lecture.